Good day, and welcome to LMR Master, VNA, and Cable Sweep Differences. We start with a picture of the front of the LMR Master. As you can see, it is a standard E-Series instrument with your number pad and most of your controls right on the front screen. Today, we'll be dealing with the VNA portion or cable sweep portion. And moving to the top of the unit, we'll be dealing with VNA ports 1 and VNA port 2. Of special note, these ports are only designed to handle positive 23 dBm of power back into them. They are not designed for any high power at all. So keep that in mind. Now, let's switch to the front screen and look at the LMR Master itself. This is using the remote control, and we are on the menu screen, and we're going to start with VNA. Now in the VNA mode, or should I say the cable sweep mode at this point, the LMR Master defaults to the field mode. Field mode has certain measurements versus VNA mode, which has different measurements. We're going to start with field mode. Now in field mode, you will find frequency distance, scale, sweep, measure, and marker. Frequency distance is always the same and very similar to the SiteMaster series. Scale is the scale of the display. Sweep is sweep controls, and then measure, what do you want to measure? And it always starts off in the measure submenu. So we're going to start first with measurement type. By clicking on measurement type, we determine which measurement we want to take. The options are VSWR, return loss, cable loss. Now those first three are one port measurements. They go in and out of port 1 only. Insertion loss is a 2-port measurement where it originates in port 1 and terminates in port 2. So it goes through something, some device, something, where it goes out of 1 into 2 through that device under test. 1-port phase is a 1-port measurement. 2-port phase is a 2-port measurement, once again going from port 1 to port 2. 1-port Smith, 1-port measurement. Dtf Return Loss, which means distance to fault in decibels, and Dtf Visuar, distance to fault in the regular scale of VSWR. Now, choose which one you want. We'll start with return loss, and we'll press enter. And then we'll go back and we'll set our return loss, starting with frequency distance. Because this is a frequency-only measurement, all we have is frequency. Now, for today's example, I'm going to use 1500 to 1900 because I have a filter that I'm going to show eventually. So if we wanted to change, we would just hit start frequency, change the frequency, stop frequency, change the frequency, or use center frequency and a span around it. As far as the scale goes, 0 on top, -50 on the bottom, that's a perfect scale for return loss type measurements. If it were a different type of measurement, the scale would be different and we'd set it up differently. If it were a Visuar measurement, for example, 1 would be on the bottom, and then we would set up our scale above that. I normally use 1 to 10 or 1 to 5, but that's up to you. Sweep controls. These are going to be very similar to your basic SiteMaster. Run and hold, obviously run. Singular continuous, well, we want continuous. And here's where it gets a little different. Data points. In your typical SiteMaster, you have 5 or 6 choices of different numbers of data points. In the LMR Master, because it uses a true VNA Vector Network Analyzer board, we can set the data points anywhere from 2 data points to 4001. That being said, more is not always better. It all depends on how much granularity you actually need, keeping in mind that every data point represents a certain amount of time for capture. So with 201 data points, it's very, very quick. It's less than a second a sweep. Whereas with 4001 data points, it could be several seconds per sweep. Averaging and smoothing, I will click on it. Most people in the field do not do any smoothing or averaging to their traces. You can if you choose, but most people in the field just want to have it, one sweep after another, the raw data that they want to see. Propagation velocity, not so important when you're talking about a return loss measurement. It becomes important, and we'll go over that in a few minutes, when you're talking about a distance measurement. And then on to output power. There are 3 levels of power: low, default, and high. And these are approximate powers. These are not dead-on powers. These are approximate powers, and everything is relative because you're going to calibrate. Default is about a -5, high is about a 0, and low is about a -25. Most people will use it in default for most everything they do. You can use it in high. Low is normally used when you're sweeping something that may have a gain to it, like a tower-mounted amplifier, where you want to input a low signal. It's not ready for a -5 or a 0 dBm signal because of the amount of gain that it's going to give. And the next one here is called RF immunity, and let's talk about that a little bit. RF immunity, high and low. It defaults to low. In the high mode, what it does is it dithers the output signal. Basically, it digitizes it and makes it so that the machine can recognize when it's its own signal coming back versus other signals coming from outside sources. This is good when you're sweeping antenna systems and you don't want outside sources interfering with your sweep. By going to high RF immunity, it does slow the trace down a little bit, but what it does is it allows for other signals coming into the antenna system, as long as they're below 0 dBm, to be ignored, basically. And last but not least here is RF power in hold, on or off. If you're not going to be switching from run to hold, it doesn't matter where you set this. The idea behind this button was for those people who are going to have a long time in between sweeps, and they don't want to shut the machine off and have to recalibrate it, they would go into hold and then have this shut the RF power off, so that all of a sudden you're not outputting anything while you're waiting to set up for your next trace, your next sweep. It's a way to save battery power. And back to measure again with our return loss. Now, in all of the E series and T series, we have the shift functions. Shift 9 for mode, Shift 8 for system. And the one that's very unique to this is Shift number 2, Shift Cal. And this is where we will find the calibration menu to calibrate for what we're doing. So I'm going to hit Shift, and you see the shift appears to the right of the battery gauge, and then number 2 for calibrate. And this brings up the calibration menu. Before we start the cal, we have to determine our cal type. There are 4 cals listed: 1-port, 2-port, 1-port response, and 2-port response. 1 and 2-port response are quick cals. For 99.9% of what you're doing, either do the 1-port cal if you're doing regular 1-port measurements, or the 2-port cal for 2-port measurements. So I'm going to enter 1-port. Now there are a couple other buttons here. Let's talk about interpolation, on and off. If you turn interpolation on, what that allows for is during the cal, when you're done, if you're going to move markers around, they will go to whatever frequency you want them. Whereas if interpolation is not turned on, when you activate markers, they will jump between data points. And the data points may not be exactly where you want them. So, something to think about. If there is some cal info on already stored, you can check it. And cal correction on. When the completion of the calibration is done, the cal correction will turn on. And by nature of the VNA board, it will try to not let you invalidate the cal by changing frequencies or other things until you turn the cal correction back off. So let's go ahead and do a standard cal. 1-port, and let's start it. In the SiteMaster series and other series, it does it one step at a time. Here, it lists all the steps. And there's an advantage to this. But we're just going to go ahead and start normally, and then I'll explain the advantage. So we're going to start, and it's very simply, it talks about open short load, just like normal. So I'm going to take my cal components here, and I'm going to hook up the open. Once I've hooked up the open, I will go ahead and press the enter key to have it measure the open. So it's measuring the open. Notice it stepped the line down to short port 2. Excuse me, short port 1. And then I would move my cal component over to short before I hit enter. And here's the advantage that you don't have with a regular SiteMaster. Had I made an error on my first one, on the open, I could actually use the arrow keys to arrow back up and do it again. So I wouldn't have to, escape out of the entire cal. But I've gone to the short, so I'll arrow back to short and press enter. And then last but not least, I will hook up my load and press enter. And the final step is to calculate and finish the cal. Press enter. You don't have to make any changes at that point. Now, a lot of people, like me, will leave the load on in place to make sure that everything kind of goes to the bottom, that we've got a decent cal. So at this point, we're ready to make measurements. And we could hook up any antenna and start making our measurements in return loss. Now, because we've calibrated for the specific frequencies, we can do any of the one-port measurements that are listed as long as we don't change frequencies. And I went ahead and put just a random antenna on here. And as you can see, this antenna is really good in the 1800 band and really horrible at 1500. And it's just a small little antenna, so no great things there. I'm going to remove, well, I'm not going to remove the antenna just yet. I'm going to leave it on. And what we're going to do is we're going to look at some of the other measurements. So at this point, we could change to any of these other ones. So if we wanted to do VisWAR, we could go to VisWAR, as long as we don't change frequencies. Now keep in mind, we did not do a 2-port cal, so going to insertion loss or 2-port phase is not recommended. But let's arrow down and let's go to distance to fault return loss, which will be a distance to fault measurement using dB. So in DTF return loss, we need to go back through and check our settings, because DTF is set up a little bit differently. We'll go back to frequency distance and notice now it's a distance measurement. So start and stop distance. Distance info, start and stop frequency, are units, meters or feet. And then under the more button here, I'm going to go ahead and click that, cable loss and prop velocity, or you can use the cable list. Now, if you click on the cable list, you will get this large list of cables. And it is rather extensive. One of the options that you have is, let's say that these LDFs right here, which are from one manufacturer, let's say that those are the ones that I use on a regular basis. I can start with, say, LDF 4-50, and I can select that or star it as a favorite. And then I can go down one and make that a favorite, and go down another one, make that a favorite, go down another one, and I can choose the ones that I use on a regular basis, save them as favorites, and then instead of displaying all of the stuff in the list, I can now just have a favorites list. That makes my life a little bit easier. So I'm going to say that I'm using the L4-50A for my cable. And notice it has a propagation velocity, and it has loss per meter based on 1, 2, and 2.5 gig. So the table is in there. Once we get the one we want, we press enter, and those settings will be applied. And of course, our windowing for distance to fault can be nominal side lobe, which is what most people use. You can use low side, minimum side, or rectangular. That's your choice. Okay. But let's go back to this one here that we skipped over called distance info. Because start and stop distance and start and stop frequency are pretty self-explanatory, but distance info is a little different. After you've got everything set up, based on number of data points, based on frequency and everything else, this will tell you how well or what you can see. If you look very closely, it'll tell you what the resolution of distance is. In this example, it's 2.1 feet, which means the plus or minus in distance will be 2 feet. Using 201 data points and our distance max of 216 feet. Now, if we had 1,000 data points, we would see significantly longer. We'd still have the 2.1 feet of plus or minus in our calculation, because the calculation is more based on how much frequency we gave it. Now, if we open this all the way up with a start frequency of 500 kilohertz and a stop frequency of 6 gig, our distance resolution would be 0.12 feet, about 2 inches. And we would, depending on the number of data points, we would not be able to see that far. With the 4,000 data points, you'd be able to see a couple hundred feet. But in cases where you might want to narrow in on a more exact where the fault is, you can add more data point. Well, you can add more frequency and data points and try to get a better resolution on things. This is just an information thing, the distance info, so when you're done with it, you just hit escape. Alrighty. Let's continue moving on. Now for VisWAR, if we wanted to change to VisWAR, it would be a different scale. And Dtf VisWAR would be in that ratio scale. Same as VisWAR. So the difference between VisWAR and return loss is just the scale that it's on. It's the same basic measurement. Cable loss, which is return loss divided by 2, is a one-port way of doing insertion loss. Now, insertion loss, you inject on one end and read out the other end. So it would have to go through something and back into port 2. Well, a lot of times, if you have a cable running up a tower, this is not practical. And that's where cable loss comes into play. After you're done with your calibration, you would put a short on the end of the cable, and that'll guarantee 100% reflection coming back. And then it takes that return loss measurement, which is whatever's coming back, divides it by 2, so that it tells you what the one-way loss is. Because there's going to be a certain amount of loss as it travels up the cable to the short, and a certain amount of loss as it travels back to the unit. So it has to be divided by 2. One port phase. If we actually go to a phase measurement, will give us phase. 180 degrees one way to 180 degrees the other way. And of course, one port Smith chart, for those people who are familiar with Smith charts, you can look at the Smith chart and how everything reacts on it. Capacitive reactance, inductive reactance. Most people in the field are not doing Smith charts unless they're designing and building antennas. But it's there for you to use if you need it. So keep that in mind. I'm going to return this to return loss for now. And we're going to talk about doing a 2-port cal and a 2-port measurement. So actually, what I'll do is we will go to insertion loss, which we know is a 2-port measurement. Press enter. Notice the cal went away under insertion loss. Now, since I want to keep the same frequencies, I'm going to go ahead and calibrate it using these frequencies. So I'm going to go to Shift Cal, and I'm going to turn the current cal off. And then I'm going to change my cal type to 2-port. And I'm going to go ahead and start my new cal. Notice, the only thing that really happens is it adds 2 steps, one that we do and one that we don't do that's optional. The one that we do is through forward, which means you're going after the open, the short, and the load, you're hooking it to the other port so that you can see through, all the way through, and everything normalizes that way. So let's go ahead and get started by hooking up our open. So the procedure is almost the same, and you still have the ability to arrow up or down to redo any one of the steps if you need to. So we'll start with the open, and we'll let it measure. And then we will move to the short. And once again, let it measure. And then the load. And now the through measurement. And last but not least, calculate and finish cal. Upon completion of all of this, what should happen is everything should go to 0. Now, because this is a 2-port measurement, I'm going to change my scale slightly, and I'm going to make my top a +10, and I'm going to make my bottom, to make everything nice and even, a -40. And that'll make my lines nice and even by 5. And you can see it's sitting right at 0. Now, I'm going to go ahead and put a device in line here to test it. Now, the first device I'm going to test is just basically an attenuator. An attenuator should be reasonably flat across the band that we're using. I just have to disconnect and hook it up. And as you're hooking and unhooking, you have to, re-verify that all your connections stay at the proper amount of torque. So, this is a 30 dB attenuator. As you can see, it's close, like most attenuators are, but it's not exactly 30 dB. So if I turn on a marker, you'll notice that if I turn on the marker table, it's at a 29.5.4. So, something to think about if you're going to use that attenuator, to maybe not use 30, but use 29.5, because it looks like it's pretty flat, at least through this part of the band that I'm using. 29.5. Okay, let me turn that marker table back off for a moment. And let's try a different device to test this time. This time, we're going to test a filter. One that's designed to filter certain frequencies and pass certain frequencies. Now, this could be a combiner, this could be a duplexer. You can tune these using the S412. Sometimes you have to balance between number of data points and time to figure out the right speed to do this. So here is our device under test, and it is an uplink filter for the AWS band. And as you can see, based on where this marker is, it starts right in the 1710 range and goes almost flat, and then it rejects. So if we were looking for things in the uplink band and wanted to reject everything else, especially the downlink bands of other things, then we would use a filter like this. And that's the insertion loss measurement. Now, 2-port phase would just be phase going through it. So we don't need to really get into 2-port phase. But I could add more markers so that I could define exactly where things are. And keep in mind, I can only control one marker at a time. But I could fine-tune this marker to exactly where it starts to drop off. Let's call it the Let me turn the table on, and we'll call it the 3 dB point is what I'm looking for, where it drops by 3. Let me go a little more. All right, right in there on the one side. It's pretty jumpy. So let's go back to marker 1, and we'll tune it a little bit. To that 3 dB point. Or the half power point. So, about 1706 to 1786, which basically means this filter covers the 1710 to 1775, 1780 range of AWS, and that includes AWS 3, which was the latest of the auctions in the AWS band. I'm going to go ahead and turn the marker table off now. And what we're going to do is we're going to change over. These are the field measurements that you've seen. All of this is the field measurements. Very similar, almost identical to your typical site master. The differences are number of data points and the fact that if I tried to change frequencies right now, it would warn me that I was going to lose my calibration. So just for an example, I'll go here to frequency, and I'll go to start frequency, and I'm just going to type in 1400 instead of 1500, and try to enter it, megahertz, and it gives me the warning. Selecting frequency beyond the cal limits will invalidate the cal. Press enter to turn off cal correction or escape to keep the current frequency values. I'm just going to hit escape. That's the bad part, or should I say one of the good things where it tries to prevent you from doing that. But one of the other advantages, because it's a true VNA, is since I calibrated 15 to 19, I could change my frequencies within that range. But keep in mind, I've only got 201 data points. If I narrow this down, it's going to use just the data points in that area. So for example, based on where my markers are, if I changed my start frequency to 1700 megahertz instead of 1500. Notice it looks like I've zoomed in, but what I've done is gone to just the 101 data points that are in this section of it. Then if I undid this part, I'd probably be down to 25 or 50 data points at that point. Let's give it a try. So let's change our stop frequency to 1790 megahertz. All right. See, now I'm down to just 46 data points. That's why the line is a little more jumpy. Now, if I were going to do this on a regular basis, I might choose to start off with more data points. Instead of 201, I might choose to start off with, say, 501 or 1001. I'm going to change my frequencies back to my originals, 1500. And 1900. And that's one of the advantages, the ability to look at just the data points of interest, if we so choose. Now, here's where the big difference is. For those who are familiar with VNAs, VNAs use what they call S parameters. S11, S12, S21, S22. Now, this is not a full reversing 2-port. It is a 2-port, 1-path VNA. So I could go into the System menu, just like I do for many other things. But instead of going into System Options or anything, I go into Application Options. Since I am in Application Options and I am in the Cable Sweep mode or the VNA mode, I can change my measurement menu between field and VNA. So I'm going to change it to VNA. Now it's going to blow out my cal. I know that because we're changing modes. So I'm going to have to recalibrate. But notice, once I did that, everything changed. I went, instead of insertion loss, to what's called S21 log mag. which is basically the levels, the log of the magnitude for S21, which means reading at S2, port 2, originating in port 1. So now all of my things do change quite a bit here. So let's start off with frequency. Now frequency, the same, other than it says domain setup frequency. And notice we could change to a distance domain instead of a frequency domain. So if we wanted to do distance measurements, we would have to go to the distance domain. Our scale, once again, is different. In this, it has more to do with what the resolution per division is. So it's 5 dB per line. The reference value is 10, and the reference line is 10. And that's the way it's currently set up. When we go to sweep, that is almost the same, except we don't call it RF immunity anymore. We call it dithering, which is what it actually does, dithering on, dithering off. But notice there's one difference here. Configure ports. And this is where we could tell the ports, the different plane lengths, if we wanted to get into that far. We could actually change it if we wanted to. We're not going to, but we could. All right. And let's get into measure. And this is where you'll see the biggest change. First, active trace, trace 1. We'll get into multiple traces in a minute. Which parameter are we looking at? S21. There's only two possible parameters, 2.1 or 1.1. 1.1 would be in and out of port 1. 2.1 is out of port 1 into port 2. It's being read at port 2 and it's originating in port 1. We're going to leave it at 2.1. We know that's a 2-port measurement for right now. Okay. What graph type do we want? Right now it's in log mag. Do we have to have it in log mag? Why, no. And you will see, once you move into the VNA world, there's quite a bit more that you can do. SWR, phase, real, imaginary, group delay, Smith chart, log mag divided by 2, which would be a 1-port cable loss, linear polar, log polar, real impedance, imaginary impedance, and even inverted Smith chart. If you don't know these, don't worry. I'm just trying to enlighten everybody as to where everything is in here. Not everyone understands all of these. Most people are just used to the regular cable sweep mode measurements, VISWAR and return loss. So, no worries there. Let me escape out of that. And once again, frequency domain or distance domain. Now, here's where it gets a little different. And you can do this in the other mode, and I'll go back and show in a minute. Number of traces and trace format. Well, how many traces can we have? We can actually show up to 4 on the screen at once in different quadrants, if we choose to. So if I went to number of traces 4, looks a little messy, doesn't it? Because it says trace format single. All 4 traces are on the same one. But I could make it a little neater. And I could have different measurements for each one. This one is log mag for S21. Now, because I calibrate, well, I haven't calibrated in this mode yet, but I could actually have S11 as well, along with another S11 and another S21, all at the same time. You can easily get confused, but you can do multiple traces doing different things based on what you need to see. And that's the whole idea. You can get as deep into this as you need, keeping in mind the only options for S parameters here are 1.1 and 2.1, which means port 1 back to itself readings and port 1 read in port 2 readings. So you have to tell it which trace, what you're doing, and the whole 9 yards. I'm going to move my traces back to just 1 so that we're not as confused. And I'm going to change my format back to single format. And of course, smoothing is still an option, just like it was in the other one. All right, The only other one that you may or may not have noticed, and I have to go back to Sweep for this, is the IF bandwidth, IFBW. In Sweep, you have a couple options here. These are the IF bandwidth options. 1 kilohertz being the default, and that's how big of the sweep signal itself is. And these options are available in this mode. If you go back to field mode, you have 3 options. You have the 10 hertz, the 1K, and the 10K. Or 100K. We're going to leave it at 1 kilohertz for the default, but that can change the speed significantly because it changes the size of the sweep signal itself. All right. Everything else is almost the same, other than you're talking S parameters now, and you're talking log, mag, real, polar, and so on. Let's go back to Shift 8, and let's move this back to our field mode. Okay. Back in field mode now. Let's go back to measure, and notice that the IF bandwidth is under measure now, not under sweep, under measure. 10 kilohertz, 1 kilohertz, 10 hertz, just those 3. It's not under sweep anymore, where it was in the other mode. Here you have prop velocity. Well, those are the basic differences between the field mode and the full-on VNA S parameter mode. There are advantages to having a true VNA board, though most people may not use the S parameters in this machine. Know that they're there, and know that they give you, even though you may not be using them, the opportunity to zoom in on data points and have a lot more data points. I hope this helps and answers any of your questions. If you have any further questions, feel free to contact 1-800-NRITSU or go to www.nritsu.com. Go to our website, type in your model number, and search for it, and then go to its page and see all of the documentation. Before I leave you, I'm going to go to nritsu.com, and we will talk about some of the more important documents that you can look up. So under nritsu.com, I will go to the search, and I will type in the S412E, and I will go to the 412 page under nritsu, and immediately to the library tab. Now you'll notice there's quite a bit here: brochures, data sheets, application notes, leaflets, white papers. What I want to point you to here is what's called measurement guides. These are guides that are very specific to certain areas of the machine. One on spectrum analyzer itself, one just on power meter, one just on the 3GPP measurements, one just on WiMAX, one on land mobile radio and electromagnetic fields, but the one we want for today is VNA, Vector Network Analyzer Handheld. And if we were to download and open that, it's all about the VNA. VNA displays, field view, VNA view, and everything else that goes with it. It gets very in-depth, so if you have questions, there's a lot here as well. Thank you for your attention, and have a great, great rest of your day.